Welcome to using Rust in your next KMP app, because I'm going to show you how easy this is. But first, all right, this is going to be a monster of a talk, so I need to be ready. So I'm Ben Chatelain. I work on the Android SDK for Ditto, and you'll find me as Fat Lad on all the things. And I'm a multi-platform developer, recovering iOS engineer. So we are going to cover a brief intro to Rust, talk about why in the heck you would do this, look at specifically a very, very simple Rust library, how to configure Kotlin multi-platform, and the code to do the bridging. And then we'll bridge it over to iOS, bridge it over to Android, and then see it in action. So first, what is Rust? Rust is a very modern language with lots of things you would find. I find it, I often am seeing things that Kotlin and Swift have borrowed that Rust has had for a while. Pattern matching is very, very powerful. They have enums like sealed classes or enums with associated types if you're familiar with Swift. And it uses traits as its like interface where you can mix code in, but they're very advanced. And it also has attributes and macros where you can do some more meta programming. We'll see a few of the attributes. Rust is a low-level language, so think of it in the same category as C++ or C. It compiles to machine code. Doesn't do garbage collection. It does have an API for reference counting, but that's opt-in. And it uses pointers and references. And there is manual memory management, but there's a lot of rules in Rust around ownership. That is one of the things that people either love or hate about it, because it's a very opinionated language. So how safe is this? Is this worth the risk in my Kotlin app? Well, we're using Rust at Ditto. Ditto is an SDK for syncing data peer-to-peer across a mesh network. And it's a dynamic network that can include many different devices, iOS, Android, desktop platforms, server platforms, and a cloud that's optional. So you can sync when the cloud's available, and if the cloud's not, it can sync between the devices peer-to-peer. That mesh I was talking about can use multiple transports like Bluetooth Low Energy, Wi-Fi, LAN if it's available, and peer-to-peer Wi-Fi is really fast, but peer-to-peer Wi-Fi is platform specific, so Android to Android, iOS to iOS. The magic of Ditto really is related to how we've integrated CRDTs as the core of how conflicts are dealt with. CRDT stands for conflict-free replicated data types. And that's what powers, so two devices can agree, will agree on what the eventual consistent state is. And then you bring more devices in and they will all end up in the same state. There's a lot of papers written on this sort of thing. And we also have a query-based API. So as you can see, it looks very much like SQL, where you can ask, how many cars do I have that are blue and so forth. And here's a picture of how you could potentially have a mesh where you have like two disconnected stores or warehouses that are only syncing through the cloud, and we call that the big peer. The small devices are called the small peer. And we also have APIs for integrations off of the big peer. We're also an official MongoDB mobile partner. They recently announced that Realm Sync and Atlas Sync is deprecated, and they're going to be retiring that in a year. And we're building a connector for that. So if you're interested, there's a wait list for our upcoming MongoDB connector. Okay, so this is why I was mentioning Ditto. This is the core of our SDK. That whole middle blue section is Rust, where we have our CRDTs, our document store, the replication and mesh transport side. And then over on the right side, we have all of our SDKs, where we have a CFFI API that'll be very similar to what I'm building here, where all of our platform-specific languages plug in. And we use that CFFI layer even to talk to our own Rust SDK. So why would you use Rust? Well, performance. It's very, very lightweight, memory efficient, no runtime unless you opt into one. There's a lot of productivity benefits, like great documentation online, useful error messages that actually tell you, like, hey, put this in there. and an integrated package manager, Cargo. But safety is the real reason why Ditto is using it. There's an ownership model where it's very clear who owns what piece of data. If something has write access to a variable, nobody can read from it. And so that allows for transactional level safety, even across threads. And so their slogan is fearless concurrency, because you have this ownership model. And by the way, if nobody has write access to something, anybody can read from it. But when there's a writer, everybody has to wait, type of thing. This kind of safety eliminates many classes of bugs at compile time. It is very opinionated. You get lots of errors saying, no, you can't do that. You really have to write things in the Rust way. But yeah, very safe. And this is why, because in other languages, if you dereference a null pointer, I'm talking native languages. And by the way, when I say native, I mean machine native, not JVM native. Pointers that get used after the memory's been freed, that'll crash your app in most cases. But that's all because this is undefined behavior where the language spec didn't specify what's supposed to happen. On the JVM, there's very specific behavior that happens, but in native lands, it's different. And the worst case is if it doesn't crash, but it continues operating and it corrupts data. So these can be hard to debug. There can be lots of security vulnerabilities, and apparently like 70% of the security vulnerabilities that have been reported are from undefined behavior in one form or another. So Rust's claim is that it can solve 70% of these if you follow its things. I'm going to be opting into a lot of unsafe things, which turns off these things, but that's kind of required for bridging. So here's a simple example. Here's Kotlin. I suppressed the warning on division by 0, but it's very clear you get an arithmetic exception. This is at runtime, but at least you know what happened. In Rust, you get a compile time error. So it's telling you this operation will panic at runtime. And by the way, this is one of those helpful things that say, just go ahead, we'll deny, we're going to do unconditional panic. Or you have to allow unconditional panic to let that compile. But that's just one of the many examples where Rust is very helpful in the error messages. All right, so let's build a Rust library. That's it. Cargo, create, lib Rust. There's two options with create. You can do a library or a binary, which is basically like an executable, like a command line. But I'm going to build a library because that's what we're going to link into Kotlin multi-platform. Okay, so here is the entire content of the library, one function. So fn is for function, add numbers is the name. We have two parameters, left and right, which are i32 or integer, that's 32 bits. Rust is very specific. You pick your size, and it's very explicit about that. We're also going to return the same type, which obviously we're just going to sum those two together. So above the function line, we have pub extern C. Pub is just saying this is public. Extern is just like in C, where you're saying that this is an external function. And the part in quotes after it is saying what type of, sort of what you want the ABI to look like. And if you had put Rust in quotes there, then that's redundant. You're saying, I'm exposing this function as Rust, so Rust can call in with Rust calling conventions. But I want C calling conventions, because we're going to use FFI and the C interop in Kotlin multi-platform to be able to call in. Note the unsafe no mangle. No mangle is saying, don't rename this function. Internally, like renaming functions and that sort of thing prevents collisions when your library is linked in with another library. You could have OpenSSL and hundreds of other libraries linked in, and in native lands there's no namespacing. So mangling is a way to prevent those collisions, but we want this to be no mangle. It's unsafe because that potentially could be a naming conflict or a symbol conflict when you're linking with other libraries. So that's a Rust attribute, the pound and square brackets. Okay, cargo.toml is sort of the configuration, kind of like package.json, where you're configuring your library. And we have to add this crate type static lib so that when we build it, it's going to output a static library. We're going to see a lot more of that static library. But by the way, what is a static library? So in native compilation, you can build a static library or a dynamic, or sometimes it's called a shared library. You could think of DLL on Windows. So a static library is not executable. It's really just accessed by the build system. It's sort of an intermediate product. It's not final and can't be ran. It just has symbols defined. There might be external symbols that need to be linked before they mean anything. And it's really just a bunch of object files, .o files that are concatenated together, because if you compile a single C++ file, you get an object file. And like I said, it can be combined with other static library files. Now on the other side, a dynamic or shared library is execute ready. I don't like to call it executable because it has no main function or no entry point. It's accessed at runtime, so it's not actually a part of your binary. And by the way, a static library can be linked in with an application, or it can be linked in with a dynamic library that's going to be accessed at runtime. Other apps potentially can, multiple apps can use a dynamic library depending on how it's deployed. And it's very difficult to split or process one. You could think of it more as a finished library. And often these dynamic libraries are smaller than the corresponding .a files because symbols get stripped out of them and so forth. So if that was too many words, here's a real-life diagram of a static library on one side. It basically has a bunch of holes in it because it hasn't been linked yet. Those things are unknown. And on the right side, we have a dynamic library. It's a bit slimmed and it's ready for sharing. Okay, ABI is the application binary interface. And this is the term that the Google NDK stuff talks about. It's talking about the actual format of that binary. So like extern-C is part of the external interface of that binary, but so is the architecture. And the Android NDK supports 4 architectures, 2 Intel and 2 ARM. The top one is the vast majority of devices, but there's quite a few 32-bit ARM ones that are out there. And there's definitely Chromebooks that run on Intel. So this is what the NDK builds by default, but you can opt out of some of those if you don't want that. But you do have to build for all the architectures that you're going to deploy to, because this isn't like Java where it's write once, run anywhere. It's write once and run on these specific things. Okay, and another term I want to mention is a target triple. This is very similar to ABI, but this is Rust and Linux parlance for the platform that you're compiling for. This includes 3 parts, except sometimes 4. CPU architecture, often just abbreviated as Arch, the vendor, the OS, and that 4th one that sometimes pops in is the environment. But it's still called a triple, even though there's sometimes 4. And by the way, AArch64, ARM64, basically the same thing, just different people call them different things. And x64 is just a shorthand for x86-64. The 2 on the right is what you'll see in Kotlin multi-platform, but I'm calling that out since we're using different tools that call them different things. Okay, so Rust Up is the tool that you use to install Rust and all the tool chains. So Rust Up target add is how you add a target for cross-compiling. I'm on a Mac. None of these are Mac, so I have to install that tool chain before I can compile for it. So we have the 4 for Android, the 3 for iOS, bottom 2 are simulators, the top one is an actual iOS device. So cargo build is how you build this tiny little library for that architecture. And you have to specify, yes, I want this architecture and that architecture, and then it generates a separate binary in separate directories. And this is what a brief view of the directory, where you have a target directory, you have the target name, and then debug or release, and then your binary. So our library is just called Rust, but a static library's naming convention is lib name.a. So sometimes you'll see Rust, sometimes you'll see lib rust.a. It depends on where, but those 2 things are kind of mean the same. Okay. So now that we've built librust, we can use this nm tool to inspect the symbols in the library. So I'm using nm and the path to librust.a and grepping for our add numbers function. And you'll see the Android one, we've got address 0. It happens to be the first thing in the binary. I don't know what the T stands for, but then add numbers name. And then we have the iOS one right below that, where we find the same add numbers, but Apple conventions have this underscore before it. So platform differences, but there's our symbol. It's in the library. This is what Kotlin native is going to link to and find in some later steps. So now we're going to configure Kotlin multi-platform. First step, Kotlin multi-platform wizard, and I'm not using Compose UI. We'll talk about why. So using Swift UI on iOS. And then configuring Kotlin multi-platform. This is bog standard straight out of the template where you get a list of targets and we're configuring an iOS binary, and it happens to have a base name of shared. So this is going to turn into base name or shared.framework. And the Android target, we're really just configuring, okay, here's JVM. Note, this is not a native target, and this is going to be very different from some other ones, specifically Android native targets. Now these, I had trouble finding documentation for. They're definitely there, but what they do and how it works is something I had to figure out. But what you have here is those four architectures, ARM64, ARM32, the Intel 2 architectures. So that's just saying we're going to build all four of those. And then for each of those, we're defining the base name as shared. Shared in that template is the name of the module where this the Chatelain native code is going to be, and then that's going to link into a Compose app for iOS and link into an iOS app for iOS, obviously. Okay, this is brief, but notice I'm configuring all the iOS and Android native targets to set up this C interops thing for something named Rust. So this is telling C interops, I want you to build a Rust library. And the configuration for this is coming up. But you can configure more than this inline, but I put all the configuration in this upcoming definition file. So the one target that's not here is the Android target, the JVM target, because it cannot talk directly to this native binary. We'll see how it gets to it in some future steps. Okay, so let's look at the Kotlin multi-platform code. This is it. So what we have here is in common main, we have an expect function add, and all the different platforms that we support, Android native main, iOS main, and Android native. I should have put just Android main on the bottom there. So the middle one is our actual function, which is going to call the add numbers native function. And the bottom one, which is Android main JVM land, we're going to stub that out. It's going to return a number for now because there's some work to do on that, and we'll see. But for now, this satisfies the contract so that it can build, because you have to have an actual for every single target you define. And I'm not ready to do the JVM bridging just yet. Okay, so now let's take a look on iOS and see how this works. Well, first up, you just hit build, and it can't find something. So take a look here. This is a linker error. So this is LD at the bottom, symbols not found for architecture ARM64. And note that when you see something like this, there's two possible reasons. Either the symbol's not found, or you're talking to the wrong architecture. In this case, I'm talking to the right architecture because there'd be a line in there that says the architecture's not found. But always go back and look, because a lot of people jump and think it's the architecture, but in this case, it is the symbol. Notice it's _add numbers. Shared framework is linking to some Rust add wrappers is trying to call this add numbers, and it can't find it. So this is a linker problem. So we take a look at the shared framework that it was actually building. This is the path to where the Kotlin multi-platform build was outputting a shared framework, and note that the shared file inside that framework folder is the actual binary. And if we do the NM tool on this, we see add numbers, but there's no address on the left side. It has a U. So I think this is undefined. It can't link this symbol. And we've got a hole in our cheese. So how do we fix this? Well, the first step is to add the librust.a to the Xcode build phases configuration in the link binary with libraries phase. This is telling Xcode, I want you to find librust.a. It actually doesn't care about the path, it just needs the name. So you can drag it in there and that sort of thing. Step 2 is in the library search paths to add the path to the output here. And this is where I took a shortcut, because you can actually configure this for each of the 3 iOS platforms, the device or the 2 simulators. You can split this and have 3, but I just put 1 in here just for the device. And that's just back a couple of directories and down into the Rust debug directory. So that tells it where to look for that file. Then you hit build, and that link Kotlin project up at the top succeeded. So now it built. So it found that file. Over in Swift, the way this comes out, the file name is calc.ios.kt. So this is the default name that it comes out on the other side. We can actually just call add, and that literally links straight into our Rust binary and returns the number. And here's the console showing that it worked. We'll see this live in a bit with a UI. So we're done. Now let's look at Android, where the story is a bit different. Because shared native library doesn't end up in the APK with the default configuration. You just hit build, and it builds something, and I was like, what is going on? So I went looking around, and I found this libshared.so hiding in Android native ARM64 directory, debug shared. I'm like, that looks right. I take a look at it with NM, it linked it, and add numbers has an address. I'm like, okay, this is exactly what I want, but it didn't go anywhere. It didn't end up in the AAR file for shared, and it didn't end up in the APK for the app. So what's going on here? Well, it turns out it was just missing something to copy it. So here's the two directories, or examples of the directories, because this varies by architecture and whether you're doing debug or release. But basically, we need to copy it from the first to the second. And I got an extra curly brace there. But if you note, the path to the destination that we're going to have is Android main JNI libs. This is a special directory where anything you put in there, and there needs to be an architecture-specific subdirectory, in this case is ARM64, will just get copied automatically into the AAR, and then when your Android archive gets merged with the app, it will end up in the JNI subfolder of the app. And it will actually inspect the architecture and tell you if you put it in the wrong place and that sort of thing. So it's a very special directory that will magically just copy it there. So all we need to do is make sure that our library has been linked, then we'll copy it there, and then we set that the merge debug JNI lib folders, which is what's going to actually grab this and put it in the package, depends on our thing. But that has to be in an after evaluate phase because that task isn't defined initially. But that's enough. If you notice on the left side, as soon as you build, it will drop it in the source tree under JNI libs in the architecture. And then unpacking the shared modules AAR file, here we have the JNI folder that I mentioned, the architecture and lib shared. If I had done this for every architecture, they'd all be right next to each other under JNI and JNI lib. But that's where we want it. That's in the AAR. That's exactly where it's going to be inside the APK. We're golden. We've got our native library. And so that is Rust plus Kotlin native in a SO file, which is a dynamic or shared library. Okay, now inside our Kotlin code over in the JVM, in our main activity, we're just going to add system load library shared. That's going to look for libshared.so and blow up if it can't find it. But it is going to look in the architecture specific directory. And also, by the way, if you have multiple architectures and you deploy through Google Play, if you use an app bundle, users aren't going to get the other architectures. They're only going to get their architecture. Okay, so that will load it, but then it's just sitting there. We need to call it. So we call calc android's add function, and the value we get back is just that stub. So now we have a problem. We have our native binary in the app. We have some Java code or some bytecode from Kotlin, but it's only calling our stub. Our calc android is not talking to calc android native. So how do we deal with this? Well, what I did to deal with this issue is create a calc bridge, and I just threw it in a companion object, and note the external keyword on this. So this is declaring that this is an unimplemented method in a Kotlin class. I'm calling it JNI add. So when you build this, by the way, is a trick for JNI development because the function name over on the native side is huge and ugly. The easiest way to figure out what that's going to be is just build and look at the error. So what happens when you build this? You have an external function with no corresponding function. You have an unsatisfied link error. So at runtime, the JVM is saying, oh, I need to go across the JNI bridge, talk to the native something, and look for something. It uses the package name of the class name, and if you're using a companion, it's got this weird generated thing, but you notice it has JNI add at the end there. Okay, now we know the name it's looking for. Now what we need is basically a C function on the native side that has that name, and it will get that call. Well, how you do this typically with the NDK on Android is not easy. It's like the simplest cases have taken me a couple days, but it's basically you have to configure the NDK, you have to create a CMake build, and you have to tell it where your thing's going to be and deal with architectures and your path, and then write some C++ code and put it in the right place and bang your head, or why am I writing C++ and so forth. But we're doing Kotlin native, right? Can't we do this in Kotlin native? We can. Okay, so this is the ugly part, is in the Android native targets back in your Gradle file, you do have to configure a new C interops thing. This is saying, here is my JNI implementation. The NDK path here, this is another hack. You would want to make this more dynamic per architecture. Instead of doing for each, you'd have to configure it by architecture. No, let me take that back. The two variables in the path, first is NDK, which is your Android SDK path, plus the NDK folder. You do have to install the NDK separately through the SDK manager, and then there's a version. So there's many versions of the NDK, and you'd need that in there. That's part of the path. But the rest of it is the toolchain path on a Mac. So in that sysroot user is two folders we care about, and that's what's highlighted down below. Include, which has the JNI header, and then include Android, which has some other things that it depends on. That's enough to tell it how to do JNI. Except for this one thing. We have to tell it what to look for. So a jni.def file, this is a C interop def file. You just have to tell it, look for this header, and that's it. The next thing we have to do is actually implement that function that it was looking for. But the cool thing here is that we have help from Android Native, the Android Native compiler for Kotlin multi-platform. And note, we have an annotation here, CNAME. This is saying export this as a C function named this. Paste that ugly JNI string in there, but notice this is our JNI add. And then we can call this function anything we want. Now the signature of this function is something that took a little Googling to figure out, but there's two parameters that are like the JNI environment, and then there's a class reference. But the last two, or anything after the first two, is the parameters of our actual Java or Kotlin function. And in this case, it's a int, or jint in JNI stuff. So it takes two jints, it returns a jint, but now return add, that is the add function for the Android native that calls add numbers, if you're following. Okay, but that's it. If you've seen other JNI stuff, it can go on for days. So this was quite easy. Okay, so this is our bridge to cross from JVM to native, and then it's going to call another native function, and then it's going to call a Rust function. Does it work? Let's see. Okay, here we have Android Swift UI view that calls calc-ioskit.add. I'm going to hit run. We're going to see a simulator. We're going to add some numbers in here and calculate. Okay, we stopped on a breakpoint. I don't know, will that zoom in? Oh, yes. Okay, so this is in Swift code. We can see our 1, 2, 3, 3, 4, 5. We let it go. That goes down into Rust, back out, and we have our number. Okay, so as far as you can go in the code, if you drill down into that, this is the Kotlin native generated Objective-C that's behind that Swift call. It is kind of ugly, and there's other ways to make your Swift prettier on Kotlin multi-platform, but that wasn't the focus of this talk. The implementation of that function is what calls the Rust function. Okay, so great. iOS works. Does Android work? Okay, so on Android, we've got a really simple calculator. Actually, let me just relaunch this. Make sure we're running the latest Oh, and I forgot to hit debug. But yeah, very simple, no numbers or no letters. I did not put error checking in, so. Okay, so here's our Kotlin add function. That calls in, gets a string back, and here we have 3, 5, 6. This add calls into the dummy function. Actually, this is no longer dumb. Calls into calcbridge, which is this external function, which there is no definition here, but I switch over to Android native. Here's that giant, ugly JNI thing inside calcbridge. Did it actually output inside calcbridge? Yes. And this calls into add numbers, which I actually love this part. If you drill all the way down in Android Studio and you get to one of these that links out, you can see the KNM or Kotlin native module file. So this is Swift's declaration for that external function, which is our Rust function. And there you have it. Okay, so it worked. Now, is it worth the effort? Would you want to do this? Now, this was a simple use case. I'm passing integers, and that was chosen on purpose because primitive types are easy. When you're dealing with an object or anything that has, garbage collection, reference counting, memory considerations, things get a lot harder when you're dealing with cross JVM to native. Because you can pass a pointer to a class, but that class can get garbage collected and you can get all kinds of errors. You can go the other way where you can pass a reference to some struct or function from native and you can blow up when that pointer becomes invalid. So those are cases where this gets really hard. But this was the point. My main point with this is this greatly simplified JNI bridging for me. I work on a Rust to Kotlin library that has really ugly bridging right now because we generate C++ and Java from our FFI API. And the C++ is ugly. The Java stuff is so weird. It does do some marshalling for us, but it's just like a pain to debug. And we've had bugs in there, and it's just not fun. It would be so much nicer to have a simple thing that's easy to understand. And I see Kotlin multi-platform as that option. It may not make any sense for your app, but it's surprisingly easy if you want to play around with it and check it out. The project that I worked on is open source. You'll see the URL to it, so you can go check it out yourself. Oh, and I have one more thing. So I didn't do much in Rust. You might be disappointed. So I have something very fun to show you the power. So here's Rust Rover. Here's our tiny little add numbers function, which is what we were calling into. I want to show you that you can actually stop on a breakpoint in native code from Xcode. And the reason why I'm going to use Xcode, I couldn't get Android Studio to work. I've gotten it to work in the past. Oops, I want to target ARch. Yes. Okay, so what I just put in here is configuration, Rust configuration, if the target architecture is ARch64. And the reason for that is I'm inserting some assembly, which is break #0, and that's not correct assembly for other architectures. And once again, I'm doing unsafe because Rust is like, I don't know what you're doing, man. Okay, so let me build this, and we'll see if it works. Kotlin native compiles do take a while in Gradle, especially the iOS ones. Okay. All right, we are on iOS. So we have a breakpoint in Xcode that we're going to stop on first before we take a trip into Rust land. Okay, here we are on a breakpoint. We let it go. Voila. That is Rust code. We just stopped on a breakpoint. Now, one caveat with this is you can't continue. So it's not that useful, except I can inspect memory. I can see what's going on. I can move this around, kind of like it's better print logging, where you can actually see what's going on. And yeah, like, whoa, not that one. But you can see here, I don't know, it's tiny, but you can see left and right, PO, right. Boom, there's our 66. So that is a superpower of Rust. You can insert assembly. Okay, if you are interested in a deeper dive in this, there was a great talk at Kotlin Conf by Solomon Brees called Using C and Native Platforms in Kotlin that goes into other desktop platforms. He didn't go into Android, and some of the weirdness is in this talk. So I wanted to plug that hole. If you want to get started with Rust, it's really easy. They have great docs, rustlang.org. Again, Rust up. That is where you start. Don't do brew install Rust. I'll save you the trouble there. Because Rust up, you can switch Rust versions. You can install different tool chains. It's super easy, even on Windows. Cargo is the super-powered build and linter and formatter. It does all sorts of things. Package manager, you publish. It's a lot like NPM, where it just kind of does everything. And crates.io is the open source community where crates are registered and you can find stuff. There's even a JNI crate where you can interact with the JNI and do bridging if you wanted to from there, but a million other things. And that's it. Here's the link to the source as it sits in this current thing, and the breakpoints that I showed you is in a branch. So feel free to check that out. Might enhance this to make it a little more friendly with the different architectures because I hacked it at the last minute. And honestly, I got the Android bridging done last night at midnight, so that was like, finally. This might be a first of Rust to these two platforms. So anyway, thank you.